I am Shambhavi. I am going to explain the topic round robin design and compare. Develop a round robin scheduling algorithm with a configurable time quantum. Experiment, compare, and justify the best quantum value by testing at least your different quantum sizes on the same process set. Introduction. Introduction means operating system scheduling means process scheduling is the OS component that decides which process on the CPU next. It aims to maximize CPU utilization, minimize waiting and turnaround time, provide fairness and meet deadlines. When necessary, scheduling policies can be primitive, can interrupt running process or non-primitive. Round robin algorithm. Round robin schedules ready process in a FIFO order but gives each process a fixed time slides quantum. If a process doesn't finish in its quantum, it is permitted and placed at the end of the ready queue. RR is fair and commonly used in time sharing system. Objectives: design, implemented, evaluate a round robin scheduler with configurable quantum. Test at least your different quantum sizes on the same process. It means to design and implement the round robin CPU scheduling algorithms with a configurable time quantum to simulate process execution using different quantum values on the same process set. To analyze and compare the performance of round robin using matrices like average waiting time, average turnaround time, number of contest switches. To determine the best time quantum that most balanced performance. To understand the impact of quantum size on fairness, responsiveness, and CPU efficiency. Next, experimental setup. Programming language. Here, using a programming language in Python and in plain single file, Python can be used to implement and simulate round robin algorithm, demonstrating how it ensures fairness and resource allocation. Tools used: any Python IDE or command line. Here is used online Python compiler. Database description, PID, experimental setup, step by step procedure. Keep a record per process means arrival time, remaining short time. First run, completion time, response time. Second, maintain a ready queue, first in, first out. Add process when their arrival is less than or equal to current time. If ready queue is empty and arrives, remain advance time to next arrival CPU idle. Otherwise, pop next PID, run it for minimum quantum remaining. On a process first run, record response time equal to start time arrival. After running, if remaining is greater than 0, push process to end of the ready queue. Else record completion time. Enqueue any process that arrival during. Repeat until all process complete. Compute turnaround equal to completion minus arrival time. Waiting equal to turnaround minus burst. Response is equal to first start minus arrival. Average values and count of contest switches. This is the flow chart of this topic. Next, I am going to explain the topic def round by robin. It processes the burst time quantum and n is equal to n in process rem min bit is equal to burst time is waiting is equal to 0 into n, then t is equal to 0. While true, done is equal to true for in range n. If remember bt, done is equal to false if rem minus bt minus I quantum. This is the output of this code. Next, annotated Gantt charts. Quantum 1 is fine timelines. These are many short segments and many context switches make span in this data set. Quantum 4 is the moderate timelines. Here P1, P2, P3, P1 it is the this shows several multi-unit slides but still primitive function fairness. Quantum equal to 8 it is a large time slides. Here, few switches, large continuous runs, small process finish in fewer permissions. Quantum is equal to 20. It is very large efficiency. First, FS here, no permission occurred. Expert or ordering behaves like FEFS for this. Observation. Here going to explain the quantitative observations like measural parameters, waiting time to WT, total time a process stay in the ready queue, turnaround time is TAT, completion time minus arrival time, response time equal to RT, first time a process gets CPU arrival time, context switches CS, times number of times the CPU changes from one process to another. CPU utilization is percentage of time CPU was actually working, no ideal time. The observations for the different quantities, it is quantum 1. Qualitative analysis means excellent response time because very process gets CPU within one time unit. Extremely high contest switching due to switching every unit time. It is a waiting time, it is a moderate high, turnaround time moderate high, response time very low, contest switches very high, CPU utilization nearly 100%. Quantum 4, Quantum 8, longer continuous CPU burst acts partially like FEFS for long jobs. Short process arriving later may wait longer, increasing response time slightly. Fewer contest switches compared to Quantum 4. Here also waiting time, turnaround time, response time, contest switches, CPU utilization. Comparative evolutions at the quantum, average weighting, average TAT, average RT contest switches, mark span CPU until 100%. Here quantum 1 16.8, it is a table of the this topic. Evolution, it is the quantum is equal to 4 means it gives the best overall balance. Quantum 1 means it gives the best response time but extremely high contest switches. Quantum is equal to 8 is moderate in all matrices, better for the long jobs. Quantum 20 behaves like FEFS, worst RT but lowest overhead. Conclusion. Round robin is a fair and responsive scheduling algorithm, especially for time sharing system. The experiment shows that performance strongly depends on the chosen time quantum. Very small quantum calls to many contest switches, while large quantum increases waiting and response time, and intermediate like quantum gives the best balance between fairness, response time, and overhead. Overall, round robin works well when the quantum is carefully chosen. Thank you.